Prakash?
Sir, shall I start, sir?
அதான் கேட்டுட்டேன். 42 இருக்கு, ஸ்டார்ட் பண்ணிடலாமா?
பண்ணிடலாம் சார். ஸ்டூடெண்ட்ஸ் ஜாயின் பண்ணிடுவாங்க சார்.
ஓகே ஓகே ஓகே. So good morning, one and all present here. I am very much happy to welcome you all to this webinar. So this webinar is on additive manufacturing, introduction to design for additive manufacturing. So it is being hosted by our alumnus, proud alumnus, Dr. Sendil Kumaran Kumaraguru. He was our alumnus. He has finished his ME production engineering from our college in 2004. So I am very glad to welcome Dr. Sendil Kumaran sir for this webinar. So I am very sure that all our students will have great benefit on his lecture. So he has got a great experience in this domain, especially in this additive manufacturing. So just I would like to brief about Dr. Sendil Kumaran. Dr. Sendil Kumaran at present currently he is working as a assistant professor in IIIT Design and Manufacturing Kanjipuram, and he has received his PhD from IIT Delhi during 2004 and 2009 from the Department of Mechanical Engineering, and he has received his ME Production Engineering, as I told you earlier. He is our alumnus in 2004, and he did his BE Mechanical Engineering in 2001. So he served as a associate professor in School of Mechanical and Building Sciences at Vellore Institute of Technology, VIT, Vellore, during August 2009 to August 2012. And he also served as a researcher, guest researcher in the US. So he is in the Systems Integration Division at National Institute of Standard Technology, NIST they used to popularly call, so Washington DC, USA, during 2012 to 2014. After 2014, he has joined with IIITM Kanjipuram, and he serves in IIIT Kanjipuram. So he is apart from this, he is a member in American Society of Mechanical Engineers, ASME, shortly and popularly called as ASME, and he is a member in IEEE. So you all very well know about the IEEE, and he is an editorial member in ASTM Journal for Smart and Sustainable Manufacturing. So he has, to his credit, he has got more than 50 publications, and he has got a citations about 626 and H index of 13 and I index of 14. So he is doing a great research in the areas of additive manufacturing, sustainable manufacturing, and smart manufacturing. And above all, so whenever we invite Sendil Kumaran, he always used to accept with always positive mood. He visit to our college as an examiner, as an guest faculty for delivering lectures like today's webinar, and he is associated with in our curriculum development. In so many ways, he has added value to our TCE, and especially in TCE academic part. So with this prelude, I welcome Dr. Sendil Kumaran to take the dais. Sendil Kumaran, please.
Sir, thanks for your good introduction. I think we still cherish the days of your class. I think I still remember some of the optimization techniques that you taught us in the ME. I think you are all great teachers. Because of the great teachers only, we were able to basically progress well in our career, as well as make some good contributions to the academic as well as research front. So thank you, sir. Thank you for being a great teacher.
Thank you for the compliments. Thank you.
Yeah, I take pride in telling you that Dr. PLP and PL, and also Dr. Chokalingam and then Dr. Jawahar, they were great teachers that time, and still they are trying to basically motivate students, organize webinars, and trying to basically connect with students and things. Thank you, sir. Thank you.
Thank you.
So yeah, I may not be able to share my videos. I have some issues, but anyway, I hope all of you are able to hear me properly and see my slides.
Yeah, sure. Yeah, we are seeing.
Okay, thank you. So I think I have even some of my classmates here, so who were with me, like I think Bruce Lee is here. I think there are many people with whom actually we had spent a lot of nice time in TC. They are also here. So thank you. Thank you for the opportunity also. I think whenever I get an opportunity, I always come and visit Thiagarajar College of Engineering. And then I had the wonderful time when I was in the campus. So it was very nice experience of me spending 2 years in Thiagarajar College of Engineering. I always cherish those memories. As Sir suggested, so we used to come to the campus anytime when there is a need, and then they invite me. So without any hesitation, I accept, and then I come because I see that as an opportunity to connect with my teachers as well as the community there. So thank you. Thank you all. So I think that the background information about this particular topic. So why are we discussing this? So why do we need to really talk about this particular topic at this point of time? Is because we are changing a lot of ways in which we are producing the objects. Like I think if you look at manufacturing in general, so there is, I think you must have heard about this term called the Industrial Revolution, the fourth Industrial Revolution. So this one technique called additive manufacturing is also part of this technologies which are actually there among the 8 technologies, which are told to bring industrial revolution. In the early 2010, like 2011 and 2012, Germany came up with a policy document called Industry 4.0 and then told that additive manufacturing is one technology which can actually become a paradigm shift in terms of how the products are manufactured, designed, used, and then retired. So it affects the entire life cycle. So that is the reason why additive manufacturing has become a, I would say, a fascination for many manufacturing people. Those who are even working with conventional manufacturing processes like machining, welding, forming, and they started working with additive manufacturing process primarily for many different reasons. So this talk, I am going to introduce you to the reasons why additive manufacturing became one of the very important techniques, and trying to give you a basic introduction to what is additive manufacturing. And then there are multiple facets in additive manufacturing. So I'm not changing slides. I'll quickly use my slides little later. So don't think that I'm speaking without changing the slides. The slides are not changing. I'm using the first slide only. Okay, so what is so good about additive manufacturing and what is so bad about additive manufacturing? Why people are embracing this technology? And then what benefits that people can accrue when they adopt this manufacturing process into their product lineup? And then we will also see what are the fundamental things that are getting changed in the manufacturing landscape just because they use this particular process. I hope all of you will have some basics about fundamentals of manufacturing, right? So manufacturing is all about what? It's about heating, beating, and treating the material, right? So you give it a shape. You take a raw material and give it a shape by heating it, by applying a force, by applying a pressure, right? So this one is little different. So let us just look at how it is different. So here we do it layer by layer. So I think most of you who are already studying about the basics, I think Professor Chucklingam would have already taught you about all these basic fundamentals. So I'm just trying to refresh it a bit so that you understand what I'm trying to convey. So it's a fabrication method. So it's basically, what you see here is basically a CAD model. So you use a digital representation of an object. So, and then you do tessellation, and then you do slicing, and then you do the part fabrication, and then you go through a number of finishing operations. So this is one simple geometry which I can, show you to help you to understand this process chain, what we call as this process chain. So let me just look at this. This is a simple CAD model of a cylinder which is standing upright on its base, right? So now I need to basically tessellate it. Tessellation in the sense like I am trying to approximate that model into number of triangles. So even though I am introducing an inaccuracy here because I'm approximating it, but it helps basically to slice this object in the next step. So it becomes easy to find the intersection between the plane and the triangles that are represented as a facet for the entire geometry. So it becomes easy for someone to take that plane and then pass those planes at different heights and then find the intersection of the plane with that triangle so that they can get the 2D layers. So here you can see that this is what the CAD model is, and then you tessellate it, and then when you slice it, you see that you get circular cross sections This is typically called as the contours, and the inside area need to be filled with hatching lines. That's what you see in the pot fabrication. And you use varieties of energy sources or varieties of methods to produce that layer. So as I said, this is a layered manufacturing. So you use varieties of techniques to basically produce that layer. So and then finally you go for a pot finishing. In fact, this process is not new. So this has been there for known for last 30 to 35 years almost. But the one of the things that has actually fundamentally changed over the last 10 years is the capability in terms of the design, right? So that is what is actually made this particular process to go from, let's say, a rapid prototyping into a final production part. So previously people were not using the final end parts out of this process, right? So but they will be only making few copies of the products for doing some test on them. So usually it's called as a rapid prototyping. So in rapid prototyping, when you are developing a product, you want to quickly test your ideas on a tangible prototype. So they would fundamentally make one or two copies of that using a 3D printer. And then they would basically do some form analysis, fit analysis, functional analysis, or drop test, or whatever it is. Like they could do some entire testing on that part so that they can commit the tooling and then go for the final manufacturing process, which may involve primary, secondary, tertiary process. For example, it could be involving some rolling process, and then maybe forming process, and then maybe a coating process. So you see that these kinds of primary, secondary, tertiary processes were there, and then people would normally use this techniques to only produce a prototype of it. Now, after 2011, as I said, so people started using this for niche applications. So it has not completely replaced all the fundamental manufacturing processes because it can never be, but it has actually replaced a few old manufacturing processes in certain cases. For we call this as niche applications, right? So something like in medicine where there is a lot of variety, right? So in those cases, people were able to basically get a good grasp of the capabilities of the process and then use that some of its advantages for their applications. So we'll see some applications very quickly before we move on to the design capabilities. So let's just look at this particular CAD model, and then the tessellation and slicing, and then fabrication. So the part that you get out of the printer directly is not usable as such. So we need to take it for further post-processing. Probably what you may want to do is to increase its finish, surface finish, or strengthen it by infiltrating with some other material, or probably you may also paint it, maybe electroplate it, or probably even use some surface modification techniques to improve the surface properties, or even some bulk properties. So a lot of things you can do. So the materials that it can process, so that's another field of research. So every week you might be seeing that some new material capabilities are being added to additive manufacturing processes. So it can have a capability to process metals, polymers, ceramics, and sometimes metalloids, and also you can use paper and glass. It's another ceramic, right? So you can also use something like sand, so which is again another type of ceramics, but I put sand separately from ceramics is the reason that it can be used to directly produce sand molds, so with a binder. So all those things are possible, all those material capabilities are developed. So then there's a proliferation of multiple technologies over the years. So and they have been classified. So this is coming from your one of the books that is widely used across engineering colleges, additive manufacturing by Professor Gibson. So he used this type of a classification. So the material that you use could be in any different starting shapes. It could be a liquid, it could be particles, it could be a molten material, or it could be a solid sheets. And then the way you are producing this individual layers. So you have seen that there are layers are being produced maybe by a high intense energy beam, or maybe photopolymerization reaction, or maybe gluing it, or maybe ejecting a small amount of polymer. So there are a lot of different process techniques available. So they can also come under many different ways in which these 2D layers are produced. You can produce one-dimensional channels, or you can use two different sources and produce two one-dimensional channels, or you can have an array of one-dimensional channels which actually moves along the X. So it's not like a hatching, but it's like one line which is actually moving, right? So, or it could be just entire layer, 2D channel, or the entire area is exposed, or entire area is the layer is produced at once. So there were many patented technologies, and they had mind-boggling acronyms. So like you have SLS here, so which means selective laser sintering. Lens here, which is called laser engineered net shaping, which is developed by Sandia National Laboratories. We have shape deposition manufacturing, developed by Stanford, and then we have SLA, which is developed by an independent company, and then we have 3D printing developed by MIT, right? So and then we have FDM developed by a company called Stratasys. So and then you have Envision Tech and other things which are based on digital light projection technologies, also called as CLIP. There's a company called Carbon which produces. So there are so many of these acronyms which were patented. They slightly modify the applications and then they patent it. So in order to avoid using these acronyms to generalize the names, ASTM has given this generic classification and then also defined many processes. So here I have a VAT photopolymerization process, which is typically having a photopolymer or a liquid in a container and then using the laser energy to selectively polymerize the monomer, because these are photosensitive polymers. When a photon can initiate a polymerization reaction and then solidify that liquid selectively wherever the light energy falls. So that way you create a very thick solid layer, which one on top of each other. So you can see that this works. So I'm not going to teach you about the schematics. I just gave the schematics so that you don't you can read it, and in your courses probably you will be reading more about this. There's a rapid prototyping course or additive manufacturing course where you will be reading about all this process and how it works, but I'm just trying to give you the lay of the land. So there could be a powder bed fusion where you are fusing the powder particles together. You may be extruding a thin filament of material by heating it and extruding it through a nozzle, or sometimes you use simple inkjet type of process where instead of ink you put the resin and then jet them, or you can pre-lay the powder bed and then use, let's say, a binder to jet. So both process works the same way, but here the material is a resin, it is jetted onto the platform. Here you have a pre-laid powder bed and the binder is basically used to glue that powder bed in a different layer. Or you can actually, sheets of papers or metals can be laminated one top of each other. And also you have direct energy deposition processes where you have on the fly melting of powder particles by a coaxial nozzle. So you have a powder stream which is coming from the sides and the laser coming from the center. So the powder gets melted and it's just work like a cladding process or coating process. So you can get a layer by layer powder deposition. So which is widely used for repairing applications and also building thin-walled components and aerospace components. And then maybe it's also a net shaping, a near net shaping process where you can build something like a near net shape and then machine it later. Okay, so now if I just step back a little and then look at it from a bad side perspective, so all these different technologies may have different process. For example, powder bed fusion, I'll show you. So powder bed fusion can have many different technologies. For example, here we have selective laser melting, selective laser sintering, electron beam melting. So there are many different techniques under powder bed fusion. Similarly, under direct energy deposition, you have direct metal deposition and laser engineered shaping. So there are minor variations in the processes and the mechanisms. So, for example, these are the two major metal laying processes, but also recently there are many different processes which can be also come under metal laying process. For example, binder jetting is a metal laying process. There is something called joule printing, which works on resistance heating. You can also have cold spray based additive manufacturing metal process, but these are predominantly more commercially used, right? So there are many different techniques available, but we are more interested in looking at metal laying process from the perspective of this particular aspects of powder bed fusion and direct energy deposition. If I look at more closely into the powder bed fusion process, there are many different mechanisms. So, so as I suggested, that you have you have a powder particles, and then you have to heat the powder particles to fuse them together selectively wherever you want to create the layer or the solid. The rest of the regions will remain as a powder, and then you can create layer by layer solid solidification of the powder particles or consolidation of the powder particles, or you can say coalescence of the powder particles and then you would normally get a three-dimensional object, which actually has a very rough, poor surface, but later it can be processed to get a smooth surfaces, right? So the mechanisms by which this can be done, there are 4 different classes. Like you can see that it could be solid state sintering, where you don't use any full melting at all. So it's like everything is done in solid state sintering. You have 2 powder particles. They are not taken above the melting point, but they are taken to a sufficient temperature where the viscous forces are used to overcome the surface tension forces. Because the powder remains a powder because of its surface tension energy, you just try to overcome that by a viscous force so that the powder particles join together and then become a solid, or like necking can begin, and then it consolidates. Like you can see here, these are the 2 powder particles, and then there is a necking, and then there's a diffusion of material, which is typically called solid phase sintering. In liquid phase sintering is also widely used, I think from 2003 to 2012, but it is no more popular. Only it's useful for ceramics and composites, but not widely used in powder bed fusion involving aerospace parts or high dense parts. But this could be also another route. For example, copper bronze and nickel bronze type of systems have been there, and it's commercially available. In India also, we had a few missions very early, like 2003 and 2004, which involve these kinds of mechanisms. So here you can use a distinct binder and structure. So material will be, 2 materials are entirely different. One will be a binder, another will be a structure. Or sometimes you can, there is no distinct material. So the same material is being used. So you can have separate structural and binder particle, or you can create a composite. Probably then what you would have done is like you would have pre-alloyed them together and then created a composite, maybe a nano composite with particles, right? So there is already, they would have made into let's say pellets, and then they would have been crushed against a ball mill, and then some intercalation exfoliation could have formed, and then it's pre-alloyed composite powder, and then you try to basically process them through the powder bed fusion. So you create the pre-alloyed composite powders, and then you glue them together. So in full melting, this is what is currently available, widely used. This is the next class of mechanism. So you use either a single component powder, or you can use a pre-alloyed powder mixture. So, or you can use different powders and fuse it at the point where you want. So, but this is not widely advisable because of the segregation and other metallurgical issues. Like so, because the powder particles, when you are mixing them, if it's not properly mixed, and then maybe you are one material may be having an high melting point, another material may be just not melted at all. For example, here you can see that the partial melting. Here you can see that in the partial melting case, liquid phase sintering, you have unmelted phases here. So this is the totally melts phase, and then the powder particles, and then you have a secondary phase. You can see 3 phases present. So one is the liquid phase material, which is taken above the melting point. Another one is remaining as a solid phase, and then when you do a sintering, then they form bonding between A and B. Whereas C is through selective laser sintering, and a preform may be sintered in an oven again to get the A and B bonding. So these are kinds of multiple routes through which people process it. So these are very old techniques, old in the sense like 10 years before they have been using it, but currently it's widely used for ceramics and other process, but not for metals anymore. So metals means like only full melting, any one of these routes. So full melting, people get near theoretical density. So they get up to 99.9%, in some cases 95%, sometimes 90%, depending upon your process parameters and your processability of the material and the capability of the lasers and all those aspects. So several process parameters control them, the amount of density and densification and the rate kinetics, all those things will depend upon it. And there could be also a chemical induced bonding. So you can actually have hydrogen bondings between binders which you can use, and then chemically bind them together. So it's just less common route. Hope I think I gave you an overall view of powder bed fusion process. Hereafter I will be starting to discuss about the design aspects of this process, so that you will be able to understand what really these processes have done over the years, why people are interested in design for additive manufacturing and things like that. So before we go on to the design aspects, I will tell you the research that is happening in additive manufacturing. You see that there are multiple research fronts. So one is in processes. People develop new processes. They work on something like, let's say, joule heating, right? So or maybe induction heating, or sometimes of some novel techniques to create that layer. So that is one research that people have been always doing. Another research is in the materials aspect, so developing a novel material with the existing processes. So superalloys like inconels, and also titanium alloys, which are lightweight, high corrosion resistance for medical and aerospace applications. So a lot of these new materials are under development. There is also a science aspect. For example, I work on science also, where we develop prediction algorithms and prediction models based on first principles of engineering. First principles of engineering means like you construct a model of the process and eliminate the iterations of trial and error. So what is happening is, like, when you're trying to produce a part with a particular strength and a dimension, so you may have to iterate until you get that strength and finish. So that iteration can be minimized if you have science-based prediction tools, where you can build first principles of engineering, like heat transfer problem, absorption, laser energy absorption problem, melting problem. You can create partial differential equations, and then maybe use a numerical technique, or an analytical technique, or an empirical technique, or a data-driven technique to solve it. So we have in fact tried all those techniques. My first PhD students did with data-driven, and then we also did thermomechanical simulations, and we also did flow simulations. So that is constructing science-based, first principles-based models, and then using that models to basically predict behavior. So people usually call this as a function. Sometimes they call it a structure, property, function, behavior modeling. So that means, like, you are trying to understand how the microstructures are evolving. Probably use a Hall pitch relation, something like which can tell you about the amount of the grain size to its strength aspects. Or sometimes you can use multi-scale modeling, like you create a single layer, single track model, and then take it to mesoscale and macro scale to create part level simulation. So sometimes people use multi-scale or multi-physics models. In multi-physics models, they also use something like flow plus heat transfer plus structural plus other functional simulations, and they combine together in one single simulation. So it's all about constructing a FEM model, or a boundary volume method, or a boundary element method, or maybe a voxel finite element method, or any type of numerical tools that they can use to understand the process properties and also the process parameters. So they would like to understand how this is like you have a fan, right? So you just rotate the knob to control the RPM, and then the fan actually rotates it. So you want to measure, let's say, for example, which is the comfort level. So you just try to set at 4-5 levels, and then try to see where you get the most comfort with the fan, something like that. So you want to basically turn those knobs like laser power, or scan speed, the speed at which the beam is moving, or probably the temperature at which you are heating it, or something like that. So you have several process parameters. So you play with those process parameters and try to understand the relationship of the process parameters with the process response. Maybe a finish could be predicted, strength could be predicted, or even strength could be many different: shear strength, impact strength, like flexural and fatigue. So all those things can be predicted, so with the reasonable accuracy, so that you don't have to basically do a trial and error, make the parts and test it, and again change the process parameter, make the parts and test it. So these kind of iterative things can be eliminated by building those models. Huge number of research groups, they work on science-based things. So I think if you remember, I told you about design, I told you about process, I told you about material, I told you about science. These are the 4 different aspects. Today I'm going to talk about only design. So I'm not going to touch upon the science aspects, or the process aspects, or the material aspects. So there are other research groups. In fact, we are also doing some little bit of polymer research in the material development, and we are also doing science-based predictions in distortion and residual stress predictions. We do a lot of residual stress prediction. We also do a little bit of process-related research, like optimization of process parameters for the functional responses. So that's we do. So those are things that very minor thing. But my research group largely works on design for additive manufacturing. Now, what is this design for manufacturability is all about, right? So I think when you, I don't know whether how many of you have gone to the shop floor and really seen these machines. So you create something in your paper, right? So you give the design to a guy at the shop floor. So in the TLC workshop, so if there is a machine operator, you give him a drawing, right? So then that person in the machine shop, he tells you like, your design cannot be manufactured here because the size is so high, or the finish that you are put in that drawing is not achievable in the machine that I have. Or you can say that the tolerances that you want on that, maybe a geometrical tolerance or a dimensional tolerance is not possible, or you have some cost constraint. So you want to manufacture that product, maybe you are going for a competition. Let's say you are in a AUV competition, or probably you have a Mars rover competition. Maybe you are going to a competition, you went to the shop floor, you gave the design, but the shop floor person says that no, this is going to be a little expensive, so maybe you put a liberal tolerance over there, or probably reduce the material usage there, or maybe reduce the size of it. So these are designed for manufacturability constraints. This is about your lathe and milling machines. Suppose you are going to, let's say, injection molding or a die casting manufacturer. So he will suggest, make sure that your parts can be split into two halves and then they can be taken out of the mold. So you have to eliminate the undercuts. You have to eliminate, what you call as re-entrant features. Sometimes you have to provide a draft angle. So these are additional things you have to take care when you're designing a part for a particular manufacturing process. So Professor Boothroyd, maybe you may study it when you go to the higher semesters. So he has made tremendous contributions in terms of understanding the constraints. So that's what I'm talking about, manufacturability constraints. He did understand each manufacturing process. He put up a constraint on geometry, tolerances, cost, function, the time, and all those aspects. He has studied them really well, and he has actually made a software also, so that you can upload a design and then give the process plan and see whether it is economical to manufacture it and what are the other constraints that you have. So this is called a design for manufacturability, right? So now, what is design for additive manufacturing and what is design for manufacturability? Design for manufacturability is I would say, a constraint-based approach. A constraint-based approach means like what is not possible in this process. When you are designing something, you always see what is not possible in that process. That is what we call as. So for example, here we have process-specific guidelines. It limits the complexity of the design. So essentially what it does is like, when you make a very complex design, so it tells you like it's not possible to make it. So let us assume this way. Let's say you are going to construct a new home, right? So you go to an architect. Architect gives a beautiful design, but the civil engineer tells you it's not possible because the design is so beautiful, but it is not constructible. Very similarly, a fashion designer and a textile engineer. So a fashion designer may want a particular draping in the fabric, but the textile engineer says technically it is not feasible. So things like this. So these are constraints, right? So people who are very creative, those who design, so they give a lot of innovative ideas. They bring it to the table, but when it is to be realized in a shop floor, so there are a lot of constraints to it. So it is not possible to produce it within the requirements of what the design engineers really want. So then this problem is like very prevalent in many manufacturing industries. And then when you commit to tooling and then it goes to manufacturing, if you are not bringing the manufacturing people early on into the design table, then there is going to be a lot of iterations and then a lot of cost, and then the product development time will be not short, and it is going to be very expensive, and also it's very cumbersome to make changes at the later point. So this is what is called manufacturability, right? So it sometimes if you see the guidelines based on the design for manufacturing and assembly, so it eliminates actually all the manufacturability problem during the design stages. So that is what the conventional approach is. So let us just look at this particular geometry here. So this is one particular geometry. Now you see that this geometry is actually developed as something called as a mist artifact. So if you see, there are multiple features present in it, and then they have a lot of tolerances being specified in this particular part. This is called as a benchmarking part. So what they do is normally they fire this test part in additive manufacturing process. Then you can tell like what features, what is the minimum wall thickness that you can have. Let's say, for example, here if I have the holes, what is the minimum diameter of holes? I have a 0.6 mm, 0.5 mm, 0.4 mm, but I would have actually produced only 0.7 mm as the minimum wall thickness, right? So, and here if you look at here, so I would have something like the gap between two features may not be more than that particular thing. So here you see the angle. So I have many different features. They are dimensional as well as geometric tolerances are specified here. Maybe the flatness, maybe the concentricity, coaxiality, run out profile tolerances, and Also, like parallelity and parallelism, and then you have perpendicularity and angularity, all those different geometric tolerances, form tolerances, all those, Renault profile tolerances and location tolerances, all those different types of GDNT. There's a separate field called GDNT, geometric dimensioning tolerancing. Probably you'll study it when you go to higher semesters. So essentially, they specify all these things in the part. So this is like, someone specifies all these things and put into the machine, AM machine. So then they can understand the capability of the machine. So the capability of the machine, it will tell what is the constraint that machine has. So it may not produce a hole which is lesser than that diameter. It cannot have a thin wall features. It cannot have thin cylindrical features, and changing areas, abruptly changing areas, step errors. So there are so many errors that additive manufacturing has. So it gives us an idea about what is that process capability. So this is what people normally do, right? So let us just look at some design guidelines which are constraint based, and also we'll also see some process planning guidelines. In fact, from 2007 onwards, I think in fact 2005 onwards, I've been working in this area. So the first paper that I published on design and process planning guidelines is around 2007. So 13 years ago. So still that is mostly constraint based approaches. So meaning like, I will evaluate the constraints of the process and also try to design it according to the constraints. So only when many design tools were developed, so the approach became more opportunistic. I will talk about it in the next phase of my lecture. So first phase of my lecture is more towards the constraint-based DFME approach, or design for manufacturability, or design for additive manufacturing approach. And the second part of the lecture is going to be talking about opportunistic part of the DFME. So what is the difference? The fundamental difference is in the constraint-based approach, I'm only looking at what is not possible, right? So whereas in the opportunistic approach, I'll be only looking at what is possible in the process, so that you can redesign it, so that you can take advantage of that particular aspect of the additive manufacturing. So it is something like that, like you would have seen some real examples of, real world examples. Let's say you are going to a machine shop, right? So, and somebody says that you want to basically machine in a lathe, and you actually always had the lathe in mind. Suddenly the machine shop guy, he has, let's say, a turn mill center. He says that I can reduce your number of setups. Could you please, we can go to the another machine where, you can have a live axis tooling, right? So which can actually produce the hole in the lateral direction. So it is like, you are actually, through process planning, you are able to minimize the cost because number of setups gets reduced. And also through process planning, you are able to basically reduce the number of, this thing. In fact, my thesis at Thiagarajar College Engineering is all about reducing the number of setups in machining. So we did a genetic algorithm based optimization there for reducing. We have found out one process plan which is the lowest cost among many different process planning in a competitive process planning setup. That was my thesis. In fact, I still remember in 2004 when we submitted the thesis. So I presented, and I still remember those things very clearly, because when there is a lot of opportunity for you to cut the cost by optimizing the sequencing and scheduling and looking at tolerance constraints and geometry constraints and other constraints, and then probably modifying your design to suit your machines and then suit your process plan, so that you can actually take advantage of the cost. That is the idea of the DFME, right? So I'll just give you an overview of the metal AM process so that you can better understand the design constraints and process planning constraints. Then we'll go to the opportunistic, right? So for example, this is a typical structure of in a metal AM machine. So these machines are little expensive. So recently they have become little relatively inexpensive because of the patent. Some patents are expired and things like that, but still relatively very high expensive when you want to use materials, exotic alloys, super alloys and titanium alloys. It's going to be a little expensive. But normal steel and other materials, it has become a little cheaper for us to buy these machines. Less than 1 crore machines were available, but otherwise it would be like 8 to 9 crores business. So that is the cost of these machines for even a very small build volume, like 400 by 400 parts that you want to build, right? So relatively they are very expensive. They are niche applications, only people use it. It's not for mass production as of now. But we'll see where the trend is going on, how it can be used for mass production and all those things in the opportunistic exercise, right? So we'll see those cases. So here, if you look at, so the first one, you see there's a CO2 laser, there's an optic, there's a mirror. So the layer by layer, the part is produced and the platform moves on, and there's a recoater. This is called the recoater, which is nothing but a blade. Sometimes they can also use a roller to basically spread the powder. So this is a powder chamber or the powder container. It actually slightly moves up so that some layer of powder can be spread on the previous sintered layer or melted layer. And the next exposure happens, and then again spreading for the next layer. Like that, the pot grows inside. You can see the cylindrical pot. This has been produced here with the hollow hole inside, right? So hollow cylinder is being produced. So because of the layers, you can see the two concentric circles, and then they fill this inside region with the hatching. Then you get the pot like this. So the procedure here is like you will have a build plate. This plate is basically called as a substrate. Right, so you can actually stack multiple pots. It's not that only one pot can be produced. You can put, let's say, 5-6 pots together on the platform, and then build them layer by layer. So this is like, at some point in time, which has built one particular layer, and then you have a cutting path and cut these pots out, and then you get this platform again milling milling, or maybe you can use a wire cut EDM to basically machine the platform and reuse it again into the machine. So this is the platform which you see. So this is the platform on which the pot is being produced here. So then multiple pots can be stocked on top of it, and then you can come to this particular area where you can see that the cutting path is typically varied. Like you can actually have a cutting path like this so that you can machine them very easily, and then you can finally produce the parts with reasonable accuracy. Okay, so now, so what are the design and process planning guidelines? I will quickly take you through this, and then I will go into the design for additive manufacturing a little later. So one of the very important thing is like the orientation. Now I think most of you can imagine, right? So let's say, for example, this particular cylinder. So when I slice it, let's say if I use a layer thickness of 50 microns. When I orient it upright like this with the base on the platform, so the number of layers is always going to be extremely high, isn't it? So the orientation is a very important problem. Last 20 years, not even 20, 25 years, people have been solving this problem of orientation. In fact, in Thiagarajar College Engineering, there are many theses on orientation itself, so optimization of orientation. So even some of my seniors and juniors, so they have done a lot of work on optimization of this, build time and cost and support structures. All those things they want to eliminate by deciding a proper orientation of the part. Let's say if I orient this cylinder in a flat way, I could have had less number of layers, but the problem is you have overhanging surfaces. I'll show what an overhang is in the next slide. So in order to avoid that overhang means you cannot build something in a mid-air, right? So you need to build supports. Let us assume you are building a house, right? So when you are building walls, you are building one brick over the other brick. So the previous brick supports the first brick, right? When it comes to building the RCC, right? So the reinforced cement concrete roofing, there you have to put a scaffolding. Scaffolding means you would have seen that people would actually provide some temporary support structures to support it, and they remove it, and then the roof gets cured, and after curing you remove the support structures. Very similarly, that is a overhang. For any overhang, even in construction that you see, right? So like that, in 3D printing also, you cannot print in here. You cannot put bricks in here. You cannot put RCC in here, right? So it's going to fall down. So you have to provide for any overhangs. You have to provide some support structures. So minimizing this supports is very important problem in additive manufacturing. I think last 20 years, people have spent a lot of energy and time to minimize these support structures, trying to only find algorithm to find a orientation where the support structure is minimum. So geometrically, they want to automate it. I think you can use your judicious judgment also. Let's say, for example, you go to a company where they have this metal A machine. You give them the part. People who have experience can actually look at this part and tell that yes, yeah. So this can be oriented this way. It should be like having less. That comes by experience. But you can also build a support system, decision support system, or you can build an advisor, or you can build an algorithm that can determine automatic orientation and packing of this parts in space, so that you can do it in less time, you can do it in less cost. Because if you have more number of layers, more time and more cost, right? So you have to fill the entire region with the powder, and all the powders cannot be used again. So you have to refresh that powder with the fresh powder, right? So all the time. So it becomes little expensive. Material wise, it is inefficient. Also productivity wise, it takes a lot of time. So it's inefficient. That is why people try to place the orientations, right? So this is one way, but the problem is sometimes when you build even though some people would like to basically have good accuracy. Let's say here in this case, to avoid support structure, these structures can be built upright. So a vertical extruded form. So this way you eliminate all the supports because the present layer can be supported by the previous layer. So this is the best orientation, even though it consumes a lot of time, a lot of material, in case you want more accurate. Because when you build support structures, when you remove it, so you will have a lot of surface defects. So that would you do not want, right? So, and sometimes the reachability, let's say for example, if you are building supports inside this, if you are building this flat, so it is very difficult for a EDM machine to reach this inside surface and machine them, because all are metal only. You are not using any separate support materials in the metal. Whereas in polymers, you can break them away because you can chisel them away because they are very easy. But we are talking about metal additive manufacturing, where this is also made of the same material. So inside, but you can actually control the density of it by varying the process parameter. But still, it is extremely difficult to reach out to this inside geometry and remove the support structure. So it becomes so cumbersome, right? So that's why people would even spend little bit money and then build it like this. So that's what one thing that I wanted to say. So some of the design guidelines I would like to walk you through very quickly, and then probably we'll go to the detailed discussions about the capabilities. Now let's say you have a small hole. This is the platform and this is the small hole. So what is happening here is like, suppose if you have a hole which is more than 6 mm, you need support structure. Suppose if you have a hole which is less than 6 mm, you don't need a support structure. So if this hole is only provided, let's say for access to something, so you can minimize the diameter of the hole. Some cases people want to reduce the weight. That's why they produce the hole. Sometimes in some applications you must have seen, they machine the inside region out because they want to reduce the weight of the component. Structurally, they want to make the component strong, but they want to have high stiffness, the strength to weight ratio. They machine something out. For example, this material may be machined out just to reduce the weight of the component. In that case, you can redesign. So you need a support structure here. So like, for example, this is the overhang. You cannot build this top region. This region cannot be built. Let me just get a pointer. So this region cannot be built, right? So now to avoid this overhang, so you can actually modify this hole like this. So if you have an angled or arced upper area, so you don't need support structure, because some angles up to which it is self-supporting. It depends upon material. For example, steel, up to 45 degrees it can self-support. Nickel, it can self-support up to 35, 25 degrees. So different materials have self-supporting angles. So you can actually produce up to that angle. So this is typically what the design guidelines or manufacturability guidelines is. Sometimes let's say you have a feature like this, a down hanging surface. Probably you will have a support structure built like this, so you can actually have a very rough surface here. So you eliminate that. So you can see, for example, stainless steel 30 degrees, Inconels 45 degrees, titanium 20 to 30 degrees, aluminum 45 degrees, cobalt chrome 30 degrees. These are the commercial, I would say, materials which are widely used. So you can minimize those. You can actually self-supporting angles. You can redesign in such a way that you have self-supporting surfaces. Sometimes you also have supports which can be also made as an offset surface. Here you can see this is the area which is machined out, probably in conventional design. So here also you can actually, you don't need to machine it out, but you can produce, modify the design. Let's say if someone comes to you with this design and you are really well known about additive manufacturing, what you will do is like, can we go to the drawing table again, and then can we quickly modify the design so that it can be successfully produced without additional cost and additional effort involved in removing the support structure. That's what most of the things. I think you must be also understanding that additive manufacturing mostly works by services, right? So because these are very expensive, not all industries can afford to have in-house. So only very technology intensive, high capital investments, those who want to afford it, they can put it. But normally medium scale and small scale industries, they use it as a service. So there may be service bureau who there are many machines will be there, and then you go to them and then give you a part and manufacture it and bring it back. So that is how the normal done. So the guys at the service bureau, so we call this a servitization or uberization in manufacturing, which is again one reason why additive manufacturing is becoming another advantage, is because you don't have to manufacture it in-house. So you can uberize it. You can send parts across the world through mail with some blockchain, and then you can protect your IP, still manufacture and get it the part back. So there are a lot of workflow chain softwares that are available. So you can make it distributedly without having to have any factory at all. So that is another reason. We'll talk about it when we come to the opportunistic part of it, right? So So here you are trying to redesign them, right? So instead of providing a supports like this, you can orient it like this to avoid some supports where the angles will be 45 degrees. Okay, so but yeah, so but what happens here is like you have the supports built in. These supports can be eliminated by having, let's say, a simple weight reduction or cooling. It can be modified as a series of semicircular, topped slots, which does not require support. So this is a redesign. So this is a constraint-based approach. So instead of this, I'm just suggesting to use this so that you eliminate the support structure, you eliminate cutting, you eliminate the need to orient it, and these surfaces can become really rough because of the star stepping and also other things. So it actually is the best design to go forward. And these are some process planning guidelines, like when you have a part and the recruiter blade is moving, right? So what normally people do is like, you cannot have the orientation of the part which is having perpendicular to it. So this is not advisable because it can actually take the part out of the platform. So because surrounding is a powder, this is the only region which is solidified. And then when a very large section which is parallel to the blade is there, so that it can actually take the part out of the powder platform. So those things can be avoided. So you can slightly orient it in such a way that only a small area is coming into contact with the vertical blade. So like L. So these kinds of things are some guidelines. Very similarly, you have long slender structures which are having such an aspect ratio which is 8:1, right? So then you can actually in between these two, when it is going to be built like this, there may be sagging and other deflection and buckling type of effects could be there. To avoid that, you can actually have a joining in the middle. And also when you have two angled cross sections which is going to meet at some particular point in a height, so it will be advisable to use something like that rather than this way, so that during the build process, it may be the supports may have to be built at certain heights, and then this may again removal becomes a very challenging thing, because machinability is a very challenging thing. The problem is once you get the part out of the AA machine, now you have to remove the supports by only machining, and the conventional machining problems all will kick in, like your tool accessibility issues, you have other issues like occlusion, you have other issues like gouging. So all those issues may prop up. So in order to avoid those things, you have to redesign something like that. This is another bicycle example which you can see, like so this is the original design, and then you can build offset surfaces like this, or you can slightly modify as a serration and build offset surfaces, or you can orient it this way and modify the design extensively. You can see this is more organic and this is more easily buildable in metal here. So you can see that bicycle pedal from a conventional manufacturing process, like let's say a forging process, and then from there you can take it to additive manufacturing, design something like this. This is what is design for additive manufacturing is all about. So you are trying to basically advise that designer, saying that you modify the design in such a way that you come to this particular point where it is easy to manufacture, and also it looks more organic, and it's like very easy to there's no need to remove support structures, and it can be built very easily, but it may consume a little bit of cost when you are trying out these parts, right? So these are things. And there are other guidelines even there, like sharp edges, because when you have sharp edge, the stresses starts to concentrate on those regions, and then the stress concentrations can produce cracking and failure ultimately, right? So also having a thin section, it may be lifted up, there may be delamination, and the angles facing into the recorder blade may cause the part to distort out of its position in the build platform. Having sharp edges is not correct, so you can see there's a rounded edge here instead of a sharp edge here. And also use the wire cut removal path some cases. So let's say, for example, when you are trying to remove the parts from the platform, so we can use some parts, wire cut parts, in such a way that simply straight cut may not be let's say suggestible, because the reason is when you have a straight cut, it is extremely difficult to understand the orientation in which the part is built, and how that part is basically built, and all you will lose all those information when you do a straight cut. So when you put an angled cut, then you know what is the Z direction, what is the XY longitudinal direction, because you must be always aware. I think all of you must remember this, that additive manufacturing produces anisotropic parts. So the Z strength is always poor because the layers are made in the Z direction. So the always the strength is poor in the Z direction compared to the XY direction. Z direction is the build direction in which the layers are stacked, right? So that is why you need to always worry about orientation of the part. You have to do always a over design. Over design means, like, let's say you have a 300 MPa strength in X and Y, maybe 150 MPa only in the Z direction. So you have to do a over design for that 150. So you have to, because its strength is very less, we have to put more material there to take care of that 150 MPa to have good strength. So that is what over design. You have more material there instead of, let's say, in one direction it would have been very easy. So so these are some of the aspects of what we call as this the wire cut path. And also sometimes the parts get tangled inside, so you can eliminate those tangled parts and things like that. And as I said, support structures, I think you all remember that we were talking about the supports. So you can see that there's a large amount of support structures needs to be built and that needs to be removed. So designing them and building them and removing them is cumbersome. So you can modify the design. Instead of like this, you can actually have a curved surface. So they can you can say that this could actually have very good things. Very similarly, when you have a support structure, you have produced. So let me just. Let me just let's say this is a small hole here. Can you see the small hole here? So this can be provided to basically have a wire cut path, because you are going to insert a wire and then do the wire cut EDM to remove that support structures in this vertical direction, right? So that way, I think you all know how wire cut electrode discharge machining works. So you need a wire. That wire needs to pass through this path so that it can be cut, right? So, or else you can put an offset surface, or you can put something like a buttress support instead of building it from the bottom. So all those things are possible. And also you can say sometimes curved surfaces. It is necessary that the downward curved surfaces has to be eliminated so that no support structures are there. And you can have many different problems. So this is what is I think a lot of people paint a beautiful picture of additive manufacturing, but it has got its lot of inherent problems. So I think in India, if you see, like, a lot of additive manufacturing research is not happening in many universities, because still they believe this process has lots of research to be done. So many industries are reluctant to adopt this because of the various problems that you see. So because it's additive manufacturing is envisioned to be a near net, not near net, in fact net shaping process, but still you need to do machining, support removal, like sometimes heat treatment and hot isostatic pressing, infiltration, and then electroplating, and sometimes you have to do sintering again in a sintering oven in vacuum sintering. So you see a lot of huge post-processing cost is involved in making the parts as good as like a wrought part or a cast part or a forged part or a rolled part, right? So people would normally like to see that the parts are net shaped products. So there are a lot of issues. That is why the additive manufacturing community in US, in Europe, and in Japan, so they are trying to address these issues. There is very active research going on, because there is a lot of advantages, which I'm going to explain you in the next part of the lecture. But to accommodate those advantages, to take advantage of those design capabilities, you need to eliminate these kinds of problems. So that's why a lot of research is happening. But in India, slowly research is picking up. So in fact, we had a lot of distortion simulation, warpage simulation. We did a lot of work on porosity and binder jetting, where we try to understand the binder to powder ratio mixtures, and then how the binder residues are there, and how could we basically debind it and then sinter it in a conventional oven. So we have done a lot of good experiments in that part. So there is also a very active research group in many IITs and NITs, and also good private universities, and they have been doing good amount of research in eliminating these problems in various processes. So what are those problems? Are distortion, because that's a thermal in nature. You see that heat source is continuously moving. So the thermal gradient is always present there, which actually causes the temperature gradient to form thermal stresses, which in turn causes residual stresses, which in turn causes shape deviations, right? So that distortion, warpage, is because of the, like as I said, in injection molding, in die casting, people don't use multiple varying wall thicknesses. I think you would have seen this guideline in Boothroyd and many different processes. So when you are making some parts with conventional processes like die casting or injection molding, so you have to keep the thickness uniform across the part. The reason is because when the pot is injected, the mold is injected with the polymer, during cooling, thick sections cool slower and thin sections cools faster. That differential cooling will create a warpage. Very similarly in die casting, when you are when you are casting a metal, maybe aluminum die casting or probably magnesium die casting or even some other die casting materials, you would normally see that when you have mixing thin thick sections, so thick sections may be cooling faster. Maybe a porosity or a crack may be formed because of the solidification cracking could be there due to uneven cooling because of thin thick sections. So normally there are guidelines to make sure that you have uniform thickness. I think you would have seen your fridge covers and you would have seen your your washing machines. Maybe when you try to open the door of the front loading or a top loading washing machine, probably you see that when you open the door of a normal top loading washing machine, you will see there are lots of ribs are being provided. So the ribs and the bosses are provided because you have to maintain the uniform thicknesses. Some sections may need a thick material because that strength is very poor there, but you cannot keep the thin thick sections in that part. So that is the reason why they provide additional bosses and ribs for added stiffness. So these are design guidelines that people go through. They add these things. And also in injection molding, you would have seen like geometry boxes, right? So we call this as pencil boxes, right? So earlier in metal pencil boxes, you will have hinges. So here, this is one single piece. You would have seen the plastic boxes. So there is a living hinge. We call this as a living hinge. That feature is very easily made in using injection molding. And also you would have seen in your backs, right? So when you are clipping two things, even when you look at your remotes, so in the remote, you are able to basically, there are no fasteners being used there in the remote, right? So it just snap fits. You just click it and it goes locks in there. So these kinds of things eliminated the need for fasteners, but they are capabilities of the injection molding process, like living hinges and having snap fits and having parts which are having, let's say, thick and thin sections is all part of this injection molding process guidelines, right? So now in additive manufacturing, and especially with metals, this is a real problem. So since you are mixing and matching thin and thick sections, because additive manufacturing, there is a lot of geometric freedom. You cannot force them to make only thick section or a thin section. You cannot force them to make uniform section because it's a highly complex three-dimensional geometry. So that case, it is becoming extremely difficult for people to basically have a distortion-less part or a warpage-less part or delamination. So all these issues has to be addressed. So it can be eliminated by 3 different methods. In fact, we did one way is to numerically predict the problem where the temperature buildup is there. Try to orient it in such a way that the temperature buildup is not happening. Try to orient and try to place the parts within the build chamber and also control the process parameters. Let's say if there is a laser energy, try to even change the scanning patterns. Let's say you are using a raster type or a zigzag type or a contour parallel type or even a fractal type. So you can change those patterns and see where the residual stresses are becoming minimum and those things. Like you can use something like a one layer parallel takes another layer parallel to Y, or maybe something like a checkerboard. So you can see that there are many different patterns have been evaluated to understand how this thermal buildup happens and how the stresses get generated and how these errors can be eliminated. So it's an ongoing research. Many papers are being published to do this. Right. So so if I look at summarize all those aspects, whatever I discussed. So most of the design rules are based on the efficiency and also based on the weak layers and also based on the part orientation and also some considerations for wire erosion process where you have to provide some holes for removal of those. And then also we have seen how to be creative with the design freedom. So now these are some aspects. Now, what are the design opportunities aspect? So this is another second part of my lecture. So I may not spend much time here, but I'll give you an overall view. So because I teach this course, a 40-hour lecture, Design for Additive Manufacturing is a 40-hour lecture course that I offer my students to my students. So I'm just giving the introductory part of the slides. This is the first slide, first lecture that I use. Then I use like 40 hours lecture to explain this entire concept to the students. In Stanford, in MIT, it has become undergraduate curriculum. So if you look at Design for Additive Manufacturing has become so important. Now it is the core course in Stanford Mechanical Engineering, and it is also a core course in MIT. It is also a core course in UC Berkeley for undergraduate students in the 3rd semester. So it has become so important at this point of time. So people have included in the undergraduate curriculum itself. So we also offer this for masters, but not at undergraduates. But I have an online portal called dfam.in, and also I have a Swayam course where I teach this online. So you can also join. I also conduct DFAM workshops, so you can also join those workshops where I discuss about many different opportunities, right? So, but let's just look at what are the opportunities that additive manufacturing presents. Initially, I told that 2011 people started appreciating the nature of additive manufacturing, why it became so prevalent. The reason is like this. So, so what happened is, like in conventional manufacturing process, the moment I mention about conventional, it's all about forming, metal forming processes and metal casting processes, and also injection molding for polymers and die casting for metals. So which is dependent on the mold, right? So you would have observed that in all this process, like casting, you need a pattern and then a mold, and then only the final geometry is obtained. In injection molding, you need a mold, right? So which is a replica of the part. Then it's a negative of the part. Then you inject polymer into that, right? So in die casting also you need a mold. In stamping, let's say the car bodies which are manufactured, right? So you would have seen some automotive factories. Probably would have went to massive percussion. So we have taken to the TAFE tour when we are at TC. You probably would have visited some automotive, maybe agricultural tractor, farm equipment, or probably a pure passenger car, or even maybe some commercial vehicles like Ashok Leyland or Daimler. Maybe if you visited some factories, you would have seen stamping process. There they use stamping dies. So the cost of these dies are extremely high. So the moment you, as I said, when some design iterations are happening, so suppose somebody wants to change the design after you commit the tooling, you have to throw away that, right? So I give this example every time when I talk about DFAM. It's about the shaving blade. So the Gillette shaving blade, the die cost is 1 crore. But if you produce, let's say, 10 lakh parts from that mold, then only that cost of the die gets justified, right? So if you don't sell 10 lakh parts, that you cannot, let's say, if you are producing a customizable, shaving razor for each and individual user, so that cost of that will be 1 crore for each one of them, because each is a different design. For them, you need a different mold, right? So then it is becoming extremely difficult to customize the product for individual users, because the geometry is so complex. If you get, and most of them die and mold is made in China. So when you send it to the mold makers there, so they will charge you something around 70 lakhs to 1 crore for one single Gillette razor. And they sell it here on 150 rupees because the cost is amortized over its volume. They are not selling it 1 crore because they have to sell that much amount of quantity to get that, cost back from the mold. Very similarly, you take die casting. So the engine, I think you would have heard about Bharat Forge, and you would have heard about Ashok Leyland. They have their own die casting factories within nearby Chennai only. So if you visit them, you would see that normally they will have they will have only 2 or 3 designs maximum, because the mold that they use have cycle times. So if you are taking, let's say, 10,000 cycles, then only that mold costs get amortized. As additive manufacturing is a moldless process. There is no mold. It's a die-less process. There is no die, there is no mold, there is no pattern. So the only support structures are needed, right? So that actually brings you, additional benefit in terms of the number of designs that you can make. So you can iterate any number of times. That's why it's called rapid prototyping. It's used in product design, because without having to have a mold, you create that very complex geometry, right? So that's why you can iterate it. And also in production process, you can suit to the customer needs. So this is what we call as the customized for the individual. So if you look at the customization angle, so you can see that you can manufacture huge number of products. Whereas conventional process, you have to achieve the volume. Volume means like the number of parts that are being produced with one particular design. Let's say I have a design. If I want to sell the design, at least I have to sell 10,000 units to get the profit margin. The break even will only occur when I sell it in large volume, because of the mold cost, die cost, and factory setup cost and other things. So I think you would have heard about flexibility, probably when you were studying about flexible manufacturing systems in a higher semester. You would have said about volume flexibility, routing flexibility, scheduling flexibility, sequencing. So you have seen a lot of flexibilities there being addressed in the flexible manufacturing system. So that is with conventional technology, but still that whatever flexible system that you have developed, a lot of issues in very complex products. Let's say I give you a very complex design, it is extremely going to be expensive to make it in machining. Even you have a very good 5-axis CNC machine, a 5-axis CNC machine is going to be expensive, and the number of hours that it takes to machine, let's say, a very complex mold cavity is going to be extremely high. So that can be minimized with additive manufacturing. That's what we'll see. So you can have a very complex part, You can customize it for individual needs, and you can actually also go for higher volume. So this is what we call as mass customization for complex products, or mass customized complex products, or mass complex products. So you can have all the three in additive manufacturing together without having additional cost. That is the beauty. So that is explained in this figure. Now, when you have a standard design, this is the standard design. So this is what the DFMA approach will give you for die casting or injection molding, or stamping, or rolling, or whatever primary, secondary machining process you have. So as you increase the design complexity, your cost skyrockets. You see that it goes up. But additive manufacturing, because it's the reason why it is less expensive is because it uses what we call as divide and conquer approach. So it is dividing that entire part into number of layers, right? So because of that, so what happens is like you are taking a three-dimensional complexity into just a two-dimensional object, simple two-dimensional layers. So that actually divides that into number of layers and divides that complexity into two-dimensional layers, so that the complexity gets addressed very easily. So that is why design for additive manufacturing increases geometric complexity without any additional cost. That is why industry wants to use this, because they have seen this tremendous potential in additive manufacturing, where you can increase the complexity at the same cost. You don't have to incur additional cost, and also personalize and also make the product more complex. The complexity, don't think only in front of the geometry. So there are 5 different complexities with which you can actually do. In fact, 4 is discussed in the text, and additional has come on. Now, so the part geometric complexity is one, or form complexity or shape complexity is one. And then you have functional complexity, and you have hierarchical complexity, you have material complexity. So all those things can be addressed. Let me just look at what those complexities are. So before we go into that, let us just take a simple die casting example here. So this example I always give it to students because they can understand really well. So you see that in a die casting, you need to add draft angles because the part has to be removed from the mold. So from the die, right? So in order to remove it from the die, you need to basically give a draft angle. So this is the design space, but you have additional design space. So this is like this degree of design freedom is not so high in the die casting. Whereas in SLM is a additive manufacturing process, selective laser melting. So in that process, you don't have to have a die, draft angle. And also there is no need to give uniform wall thickness, but here you can have mix and match. So there is a weight reduction. There is also a very high design freedom. And also undercuts, these kind of undercuts are very difficult to remove it from the mold. So because the mold, when you design like this, then it is very difficult to remove it from the mold. So those undercuts has to be avoided in the die casting. But here you can have consolidated parts in which there is no die, there is no part removal from the die, so there is no issue. And also small distance between features is not possible in die casting and injection molding. Here it is also, so you can see the exemplary benefits. The exemplary benefits are like reduction in design space, weight reduction, consolidating multiple parts together, and also again the reduction in design space. These are some of the advantages. So what are the major drivers? As I said, for additive manufacturing is the mass customization. I already explained what is mass customization. Is like you are able to mass produce the components at the same cost of a customized, mass produced part. So you are producing customized parts at the cost of a mass production. So that is mass customization. And functional integration. Like you would have seen, now people are trying to bring multiple functions into one part. So I think I have not shown you multiple examples from real world case studies. You can just go to Google and type, functional integration. You would see excellent amount of, I would say, examples of people functionally integrating parts together. Like they would have flame retardance property, electrical property, acoustic property. Let's say you have a car body, right? So now I want to print, let's say, a batteries inside my interior surface. On outer surface, I want to print my, let's say, photovoltaic cells. And in between, I want to have a structure, a lattice structure, which can actually, is a phononic bandgap material, which can only send certain frequencies of sound so that there is no noise in the cabin. So one single structure, one single 3D manufactured structure have multiple functions. So it has got, acoustic shielding or acoustic function. Also, it has got, energy storage function by printing micro batteries. It also got, solar energy generation function with solar cells. And also it has functions like, impact energy absorption from the shock, right? So then you have structures for that. So you can see that you can actually have multiple structures. So heat transfer, cooling, and also you can put electrical, optical, acoustic mix of properties. So you can have functional integration into the part. That's possible. And also flow optimization, like you can have conformal cooling channels. Because drilling process, you can only drill straight holes. Additive manufacturing can have complex cooling channels, so you can have flow optimizations can be done. And porosities can be changed. So you, let's say you would have heard about powder metallurgy process. Powder metallurgy, they make gears and other things because it can actually inherently have a good frictional tribological properties because of the inherent porosity present in the powder metallurgy. So they exploit that. So you can also tailor the porosities in medical applications like implants and other things. So you can also consolidate multiple parts into very complex ones. This is another example. For example, GE has demonstrated multiple things. If you remember, I showed one initially in my slide, GE fuel nozzle, when I introduced metal AM process, where it is 17 parts gets integrated into one, and then 13 functions got integrated into one. And the total manufacturing cost come down by 40%. And also the number of parts came down by almost 350%. So those kinds of reductions are possible. So these are the complexities which I was talking about. So shape complexity, where you can include lots of freedom in the shape. And then hierarchical complexity, where you can have hierarchical structures. In one scale, the same structure repeats in multiple scales. Material complexity, you can have, as I said, batteries, you can have PVC modules, you can have sensors. Now, I think you must have heard about this term. I think many of you must have heard about the term that in addition to additive manufacturing, you also have IoT, Internet of Things, as one of the very important aspects of fourth industrial revolution, right? So there you need to have, IoT is nothing but 4 different things. One is having a sensor to collect data and then transmitting it over network and then doing analytics in cloud and then presenting the results in a dashboard or probably a prescriptive analytics or predictive analytics. That is what IoT is all about. IoT needs physical devices also. For example, you need a sensor. That sensor can be directly produced using additive manufacturing. And you need a network, for example, any RFID antennas or any other antennas, probably circular antenna. In fact, I ran 2 imprint projects on 3D printed antennas. So one is for energy harvesting applications for military, and another one is also I'm doing it for sensing physiological parameters in soldiers and training and as well as in the front field battle. So I run 1 crore project on just integrating that function of sensing and transmitting data, IoT plus additive manufacturing project. So there are huge number of opportunities in terms of how you can actually add materials, electronic material, functional materials. So there is another field which has recently come, which is called 4D printing, where you can actually add metamaterials also. For example, function materials which has certain functions, like nitinol, which can strain gauges, which has a sensing function. You have thermally activated devices, MEMS, lab on a chip. So you have PVCs, photovoltaic cells. So you also have batteries. You have bus bars, interconnects, and even moving parts like motors. So things like that. So you can actually 3D print everything together. So that is what is functional integration. And you also have many different complexities. For example, we are producing flexible electronics, thin sheets on a polymer sheets. So these are like flexible electronics, wearable electronics. You can see that you are producing circuits on a flexible film, strain gauges on a flexible film, and things like that. So like a lot of wearable devices can be made. So these are things which are coming up, recent applications. And you are adding functionality, and also doing part consolidation and things. Let us summarize here. So with this slide, this is the last slide I'm going to show. Then I'm going to take your questions. So which gives you, it's a busy slide. This I have been using it for many years to explain the benefits of design for additive manufacturing. And then each one of them is my lecture. For example, form complexity, I ran 3 lectures. And then hierarchical complexity, I ran 5 lectures. And then parts functional complexity, I ran 10 lectures. And then material complexity, I ran 7 lectures. So these are like many applications, but this is like what the lay of the land for DFAM is all about. So if you look at my course, I tell them about the geometric complexity which is possible. So here I tell them about how to basically use topology optimization. The topology optimization is something like where you can actually optimize the material use within a space subject to a set of constraints and loading. So I'm trying to minimize the compliance so that I can remove material. Probably when next time I get an opportunity, I can also demonstrate softwares which has this capability. For example, recently, ProEngineer, ANSYS, ProEngineer is right now called Creo Elements. They have acquired a company called Entopology, right? So there are hundreds of such software tools for DFAM which has recently come, which is industry has adopted. Maybe I can give Fusion 360 generative design example. I have a case study. If you give me 1 hour, probably I will use my research scholars and give a very good, hands-on exercise also. You can practice it actually. So the problem will be created, a topology optimization problem will be created, and it can be solved in a cloud. So you don't need even a very good systems for you to try it out. So probably I'll discuss with Palniappan sir. Probably we'll do that later sometime. Maybe hands-on exercise on some of these tools which we use. Okay, so these are some of the form complexities and hierarchical structures like porous structures, lattice structures, mesoscopic structures, and material complexity like different materials into one pot, and FGMs, functionally gradient structures, where you have different types of what you call as materials which are graded in nature. Like you have copper nickel system. Copper is 100% in one edge, and then nickel is 100%. Then you have a continuous transition between the compositional. So that is kind of compositional heterogeneity can be added. And then functional complexity is about consolidating the parts and the extension of the functions, embedding foreign components like sensors and other things, right? So you have lots of this indirect value propositions. You can actually have a lot of other benefits. Like if you look at each one of these theses, like IIT Madras, I know Professor Sandra Pandian, he also comes from Thiagarajar College of Engineering. Is a proud alumni of Thiagarajar College. He has 5 PhD students. Everyone is working on one problem. For example, one student is working on understanding damping characteristics of lattice structures. Another one is working on energy absorption. So when there is an impact loading, so if you have a unique structure using additive, how the energy can be impacted. Other one is working at isolation problems, like noise isolation and acoustic problem. So improving design and aesthetics is another issue. Weight reduction or lattice structures or lightweighting is another strategy by using repeated structures and things. Ergonomics and flow dynamics, like there is a heat transfer problem, like having complex network of channels in a hydraulic manifold, or any other cooling problem like mold cooling and other things. So having that. So flow dynamics, energy conversion, all those aspects are being studied. People are developing new tools and software to design components, specific components for specific applications. Like there is a design software for implants, there's a design software for hydraulic manifolds, there's a design software for designing turbine blades, there's a design software. So every design can be uniquely tailored to the needs of additive manufacturing. So there are a lot of opportunities for you to basically design it for additive manufacturing process. Now there are also companies which actually, like 3Yourmind and other companies, they go to any company like who have thousands of parts. Like say they go to Volkswagen and tell them like I can redesign some of your parts to increase the efficiency. Aerospace companies, even like Rolls-Royce, and we have actually trained many aerospace companies in our lab. Like they have come here and understood how these techniques and tools can be applied to reduce the weight and reduce the mass, and then it could be basically optimized. So these are things that the industry does. They're developing a lot of use cases. Like we did a engine bracket case study. We did also a joint T-joint case study. We did a lot of case studies with the cycle company, TI Cycles. So many industries are approaching us. We are also training the service bureaus on some of the DFAM aspects and things like that. So you can also learn more about it over the internet. There's a lot of material available. You can learn and you can understand what are the various benefits of this. Right? So thank you all. If you have any questions, I'll be able to answer it. Okay. So, and most importantly, this field is very new, but there are a lot of commercial packages which has come in last 3 years, and you can actually try practicing your hands. Many of them offer trial licenses. You can download those trial licenses and try to modify, take an existing design which is there for machining or let's say a casting, and then modify it to suit it for additive manufacturing. What are the design capabilities that you can add? What are the additional capabilities and functional complexities that you can add, and then redesign it, and then maybe present it in a conference, and then maybe you can even do a small project work, do an internship, and then to industry, and then showcase them, and they will be happy to take your idea and then redesign some of these parts. So I wish you all a successful learning experience. I just opened up an area for you to explore. Now you can actually explore on your own many of these things what I have discussed. If you have any questions, whatever I discussed, please ask these questions. You can put it in the chat window, or you can unmute also and ask. And thank you, Dr. Palniappan sir, for offering this opportunity.
Okay, thank you, Sandil. So we are very much happy to work with you. If any chances are there, we are always ready to work with. Hello.
Yes, sir.
Yes, sir. Yes.
Yeah,
Yes,
fine,
sir.
fine.
So if there are no questions, sir, I think I leave it to Dr. PL. So I think there is some question from Dr.
Yeah,
B.
one
Bala.
question.
Okay, is there any specific method for processing of composite materials? So I think composite materials are being processed through all the routes. So not just powder bed fusion, not just sheet lamination, not just direct energy deposition. So all the routes, but FDM is most preferred route, especially for this FRPs, right? So fiber reinforced polymer composites, and particulate composites also, ceramics and all. The powder bed fusion is the preferred route. And binder jetting has recently become most popular route for metallic composites, and they are looking at even making tools. Yesterday, in fact, I reviewed many DST proposals, which has come for the recent call for the grants and other things. I have seen people are proposing to basically make cutting tools through this additive manufacturing process, through composites. Like you might be knowing about the composites that are used. So cermets and other things, they are trying to manufacture them through the additive manufacturing, because you can have complex network of channels through which the coolant can be passed. So there's a lot of very interesting ideas are being coming up right now. So you can actually explore that. So that is possible, yes. Okay, sir. Thank you all.
Thank you, sir. Sir,
Now I request Professor T. Prakash to propose the vote of thanks. And before that, Sendil, it is very nice to know that in tool engineering also, rapid manufacturing is into it, as you said, for cooling and all. It is a very interesting one. Thank you.
Thank you. And thanks, Doctor. I think I want to see Bruce Lee as Dr. Bruce Lee. I hope you receive. Okay, thank you all.
Sir, thank you, sir. Sir, once again, warm greetings to everybody. It's good time to propose vote of thanks. It's a great honor to me to propose vote of thanks. So first, I would like to thank today's resource person, Dr. Senthil Kumaran Kumaraguru, Assistant Professor, Department of Mechanical Engineering, Indian Institute of Information Technology, Design and Manufacturing, Kanchipuram, for his excellent and informative webinar. Sir, thank you, sir. Thank you very much for your continuous support towards TCE. I can say you are one of the pride of our TCE. Thank you, sir. Thank you, sir. And I record my sense of deep gratitude to our TCE management and respected the principal, Dr. Mercy Sonali ma'am, to allow us to conduct this kind of webinars. Thank you, ma'am. And I am extremely grateful to our beloved head of department, Dr. K. Chokolingam, sir, for his continuous support and guidance. Thank you, sir. So I express my sincere thanks to all deans, HODs, and faculty members of TCE. Thank you all. I express my sincere thanks to Dr. PLK Palaniappan, sir, Professor of Mechanical Engineering, one of the organizers of this workshop. Thank you, sir. Without you, this program won't happen. Thank you, sir. Finally, I would like to thank all mechanical engineering faculty members and students for their active participation and involvement. Without your involvement, this program won't get success. Thank you all, and we will meet on other webinars. Thank you, sir. Thank you all.
Hello, Sendil. This is Palaniappan. And additional information, today Chokolingam sir could not join as the registrar. He has to be in an online tender opening.
Okay.